Thanks for coming to the talk. I'm going to tell you about a paper we wrote about a year ago called NTRU-based FHE for larger key and message space by Robin, Chungyun, Hilder, and me. So what did we do in this paper? We started from final, which I'll explain later, and we added the NRU CMUX to that. We also added approximate decomposition, and we added programmable bootstrapping. And then after all these improvements, we compared it to the other state-of-the-art NTRU-based scheme by XZT, etc. Okay, so before starting to explain what final is, I have to explain what, amongst others, LWE is. LWE, or learning with errors, is an encryption scheme based on the learning with errors problem. So the secret key is multiplied by a huge matrix, and then we add to that some noise and the message. We lift the message over the noise so they shouldn't interfere, and then from A and B it is hard to get back the message because there is some noise added to it. So as long as the noise stays small enough, you can easily decrypt it. This scheme is homomorphic. However, the noise increases, as you should know. And then you need to do bootstrapping to refresh the ciphertext so the noise stays small enough. Another scheme I have to introduce first is NTRU. The name comes from a pun on Toys R Us, but this is number theorists are us. And it is an encryption scheme. Ooh. Yeah, it is. It's an encryption scheme based on lattices, so based on the shortest vector problem. So it is also post-quantum secure, which is nice. We use polynomial representation of vectors in the lattice, so it's actually mathematically on polynomials. This scheme is also inherently homomorphic, but in order to be homomorphic, the parameters need to be overstretched, which is actually an insecure parameter choice. So the ciphertext modulus needs to be very big to be homomorphic. So then comes final. Final is an FHE scheme based on both LWE and NTRU. So the actual encryption scheme is LWE, but the NTRU, or actually NGS based on NTRU, is used in the bootstrapping. And final can be homomorphic without being overstretched, which is nice. And so final is the paper on which our paper is based. Our paper improved this one. So then I need to introduce NGS, another one. So I'm not going to go too deep into the maths of it, but so we have two types of encryption: a scalar encryption, where the result is a polynomial, the ciphertext. We have a vector encryption, where the ciphertext is a vector of polynomials. I'm not telling you the decryption here because we don't need it in final, actually. And I should also say that there's an external product, which is a product between a scalar encryption and a vector encryption. The result of that is also a scalar encryption again, and doing that uses FFTs, fast Fourier transform. So just to give you an idea of the order of magnitudes of the parameters, we have plain text modulus small p, which is usually 2. The ciphertext modulus q, and also an LWE ciphertext modulus small q, which are these sizes. We have a polynomial degree, which is about 1024, but it needs to be prime, so it's about 1024. Then we have a decomposition base and a L, which is the vector ciphertext dimension, and these are about 8 and 7, roughly. So how does the final bootstrapping work? The first step is to encrypt the LWE ciphertext in NGS. The second step then would be to homomorphically decrypt the LWE encryption. And you do this by getting the inner product of the ciphertext with the key, homomorphically in NGS. And then we switch back to get an LWE ciphertext. So this is the bootstrapping algorithm. So as I just said, there's the scalar encryption here. So we encrypt the LWE ciphertext to an NGS ciphertext. Then we use a blind rotation, which takes care of the multiplication with the key. So that's actually the decryption, sort of, the LWE decryption. And then we switch it back to LWE. What is a blind rotation, though? A blind rotation is the rotation of a polynomial by a certain amount of places, so k positions. So in the clear, you could easily do that by multiplying with x to the minus k to move it k positions to the right. But to do it blindly, so where both k and the polynomial are encrypted, it's a bit harder to do. Then in that case, it uses iteratively the CMUX operation. What is a CMUX operation? So the binary CMUX is the normal case. You might know a CMUX from just actual hardware, not encrypted. So then you have two inputs and a selector bit. The selector bit chooses which one of these two will be the output. You can write it as this formula. But so to use this in final, in the blind rotation, the selector bit is an NGS ciphertext, a vector ciphertext, and the inputs are scalar ciphertexts. So what we did actually in our paper to improve on final is that we studied if it's possible to add an n-ary CMUX instead of a binary CMUX. So we extended the CMUX to get n inputs instead of just 2. We get this formula then instead, and instead of a selector bit, we have now a larger number. And we'll actually see that B in final is the secret key. So using an n-ary CMUX allows us to use a larger key space in final. If we have a larger key space, then that means we need less or fewer CMUXs, which means we need less FFTs, because we need less external products. However, the CMUXs are more complicated, so there's a trade-off there. So then we checked if it's actually good to use a higher key space. So as I've said, you get less FFTs, but you get more pointwise multiplications. That's where you multiply two vectors pointwise. If we define alpha as a measure for the cost of an FFT compared to a pointwise multiplication of the same length n, of course, then we can say that depending on the alpha depends on the implementation of the FFT, so on the library. Depending on alpha, it can be beneficial to actually use a larger key. So here I give a table. You can see depending on the P, of course, and the key size, you see that it's beneficial for alpha values of at least this. The largest value we have here is about 11. So we can actually say that if an FFT is not at least as expensive as 11 pointwise multiplications, then there's no use in getting a larger key space. Practical values of alpha, we tested a few of them for some C++ and Rust libraries, are actually quite a bit lower than 11. So we actually proved that it's not very useful to use larger keys, but we do say that it's possible. That was the first thing we changed on final. The second contribution we had was adding approximate decomposition. So in every external product, we use a decomposition noted by the fancy G. And we found out that we can actually remove k least significant words, where k can be found through this formula. And if you remove k least significant words, then you actually save k forward FFTs and pointwise multiplication. So it only comes at the cost of very limited noise growth. So actually it's kind of free. So you can just save a lot of FFTs and pointwise multiplications for free. However, in practice, k is just 1. So it's a limited improvement, but still you save 1 out of, usually the length is about 10, so you save 10% for free. Then the third contribution we had was the programmable bootstrapping, and that's where you add a operation or a function during the bootstrapping for free on the ciphertext. To do that, we first need to encode the function or a lookup table of the function into a polynomial, and then such that each coefficient of the polynomial is a value in the lookup table. And then you can add it into the bootstrapping algorithm. So over here we have this one in the bootstrapping algorithm I showed you earlier. If you replace this polynomial, which is just all coefficients are 1, with a polynomial of t, then you just get programmable bootstrapping for free. So it was actually already known that that was possible. We just proved it, that it's possible. And then as a final thing I want to say is that we compared our final plus, we call it, so final with all the improvements, to the other state of the art, which was XCD. To be fair, we also applied our improvements, so the proximity composition, we also applied it to the XCD, just to be fair. Still, it's very hard to compare the two because we have very different parameter choices to be secure. So we tried to find similar parameters to make it fair. So we chose for final a k of 3 because we have a uniform key space, whereas XCD actually has a Gaussian distributed key. So we needed to choose a k is 3. We used the parameter set that they provided, and then we chose our own, which is similar, but ours is slightly better because we have a better decryption error probability. And then we find this. So if we fill in the parameters we found, then we find that we needed only 1/3 of the FFTs that the other scheme uses, but at the cost of that we need more than double the pointwise multiplications. And also we save, we only need about 83% of the memory that the other paper needs. So that's also an improvement. So based on these two numbers, we can say that actually final plus would be better than the other one as long as alpha, so the cost of an FFT, is larger than about 1. So if an FFT is more expensive than a pointwise multiplication, then final is better. So finally, to conclude, so final with an NRE CMUX can be beneficial, but it's quite rare. Final and the other scheme can both be improved with a proximity composition. Final can easily be extended with programmable bootstrapping, and with the final improvements, final is actually better than XCD. Yeah, that's all. Thank you for attending.